This tutorial will cover one-way ANOVA. I recommend that you follow along in the workbook, but for this example, we'll be following the steps in the workbook, but using a different data set. Imagine that we've read and done some research that looks at the relationship between birth order, firstborns versus laterborns, and batting average. Now, this is actually based on real research conducted by my colleague, Richie Schweigenhoft. But let's say we want to know a little bit more about birth order, so instead of just looking at firstborns versus laterborns, we collect data in which we've got firstborns, middle children, and youngest children. So in this case, we've got a nominal variable with 3 groups, and we've got some interval and ratio outcome data, specifically batting average, GPA, both ratio data, and then need for achievement, which is a 1 to 10 rating scale on people's need to achieve. That's an interval scale. For data such as these, we would calculate one-way ANOVAs. To do that, we'll go to Analyze, Compare Means, and then we're going to start with means. Now we're going to send our grouping variable. If we had an experiment, this would be our IB. In this case, we do not have an experiment. And then we would send our outcome variable, or in an experiment, our DV, over to the dependent variables list. I'm going to click on Options, and I'm going to request an ANOVA table and ADA. So that's going to give us our test for statistical significance as well as our effect size. And then I'm going to click OK. In the output, descriptive statistics are provided under Report. We see the mean, standard deviation, and sample size for each of our groups as well as for the total. And then we have the ANOVA table, which reports the results for our one-way ANOVA. Here we see that we do have a statistically significant difference in our groups. Our p-value is 0.003, and that's under 0.05. We also get our f-value and our degrees of freedom that we would use in our report. Shown here, you can see how we would report our results of the one-way ANOVA. Click pause if you need additional time to figure out where these numbers came from. Under measures of association, we get the effect size. Eta squared tells us the proportion of variance accounted for. In this example, eta squared equals 0.11. That indicates that 11% of the variance in batting average is accounted for by birth order. Now, when our F is statistically significant, as it is in this example, we need to conduct post hoc tests. And we will also need to interpret and write up the results of these post hoc tests. To do that, go to Analyze, Compare Means, and then one-way ANOVA. And we're going to send our birth order to our factor. So our grouping variable goes to our factor box, and then batting average, our outcome, goes to the dependent list. And then second, we're going to click on post hoc. And then we have many options for post hoc analyses. I like to do LSD. Click LSD, click Continue, and then click Options. And then under Options, we already have descriptive statistics from our previous analyses, so I don't need to click that again. You could if you wanted to. I'm going to click on the homogeneity of variance test, and then a means plot. And then I'm going to click Continue, and then OK. Then we see our output. First, we'll see the results for our homogeneity of variance test. This is Levine's test, which will tell us whether or not we've met the assumption for equal variances. In this example, our p-value for Levine's is over 0.05, therefore we have met our assumption of equal variances. The next table are our ANOVA results, which is a repeat of information we got from our first analysis. Then we'll see the results for our post hoc comparisons. We'll come back and talk about that in more detail. And then finally, we get a graph of our means plot. This tells us the pattern of the results. Here we see that the youngest group had the highest batting average, followed by middle and then firstborns. But to determine if the differences in these groups is statistically significant, we need to look at our post hoc results. Under our post hoc tests, we see the comparisons for all of our groups, and we see the information repeated. We would look at firstborns versus middle children, and our p-value is 0.024. That is under 0.05, so that is statistically significant. Firstborns versus youngest is p equals 0.001. That's also statistically significant. Then we would skip the next one because it's a repeat and look at middle versus youngest and find our p-value of 0.256, which is not statistically significant. To interpret these results, we would look at either our descriptive statistics from our previous analysis or look at our means plot. If we apply what we learned from our post hoc comparisons to our means plot, we would interpret the results as follows. Firstborns have the lowest batting average, and their score is statistically significantly different from both middle children and youngest children. The difference between middle children and youngest children is not statistically significant. Now let's conduct one-way ANOVAs for our other outcome variables. Go to Analyze, Compare Means, Means, and I'm going to send birth order to my independent list, and I'm going to send both GPA and my need for achievement measure to my dependent list. Click Options, ANOVA Table in ADA, click Continue, and then OK. In the output file, we see the results for GPA and the need for achievement right next to each other. Notice that for GPA, the F value is not statistically significant. Therefore, we would not run any additional analyses and we would write up the results as we have them here. However, for need for achievement, we do have a statistically significant F value, and therefore we would need to run additional post hoc comparisons. Go to Analyze, Compare Means, One-Way ANOVA. Send your grouping variable or IV to Factor, your DV or outcome variable that you're running post hoc analyses on to your dependent list, and then click Post Hoc. Again, I'm going to do LSD. Click Continue, and then click Options, Homogeneity or Variance, and Means Plot. Continue, and OK. The test for homogeneity of variances indicates that Levene's is statistically significant. When we look at our descriptive statistics, we see that the standard deviation of the middle group is much higher than the firstborns or youngest groups. This suggests that there's more variance, and therefore there might be another factor impacting the middle group. We might also want to make sure that there's not a data entry error. In this case, there are no data entry errors. The means plot simply displays the descriptive statistics in a graph. Here we can see that the middle children have the lowest rating, and the youngest and firstborns have higher ratings. We'll need to look at the post hoc comparisons to determine if any of these differences are statistically significant. The post hoc tests reveal that there was a statistically significant difference between firstborns and middle children at p equals 0.02 when we round. You might recall from looking at the graph and the descriptive statistics that firstborns had a higher score on need for achievement than middle children. The difference between firstborns and youngest children was not statistically significant at 0.79, rounded again, and the difference between middle and youngest children was statistically significant at p equals 0.03. Remember that the youngest children had similar scores to firstborns and a higher score than middle children. This concludes our tutorial on one-way ANOVAs.